Okay, the last part of the lesson looks at graphing transformations. So now that you've seen how to write an equation in vertex form, now we can look at how to graph transformations. One of the methods you used last year was the step pattern. So I'm going to jump down here first and just review the step pattern with you, and then we'll go up and look at the new method of graphing. The step pattern, you know that the equation must be in vertex form. And we use the vertex and patterns between the points to graph the transformed function. This is a great way to check your work. Unfortunately, in this course, the step pattern will not be very ideal. Part of the reason for that is because you are learning many different functions, and each function would have a different pattern between the points, and remembering all those patterns would be very challenging. Also, the step pattern changes drastically because instead of moving over one and then up a certain amount, or over two and up a certain amount, the amount that you move over will also be changed. So essentially, that's the reason why we're going to look at a new way of graphing, and that way of graphing looks at mapping notation. Okay, this isn't very different than what you were doing in the step pattern, in the sense that when you were using the step pattern, you would multiply the pattern numbers, whether you're moving up 1, up 4, up 9, etc. You're multiplying that by whatever the value of A was. Now in mapping notation, this is something very similar to that, but we also look at the horizontal shift and the vertical shift, left and right and up and down as well. So in mapping notation, the equation must be in vertex form. So you want to be able to see all the different transformations that are applied to y equals x squared in order to create the new function. What we're going to do is create a new set of points by applying the different transformations to the key points of the function. So depending on what your function is, so in a quadratic function, you're going to have a specific set of key points. Those key points will help show the curvature in the graph. So for a quadratic relation, what you want to be able to see is that it creates a U-shaped curve. Okay, so we're going to have a set of key points that we're going to use, and those key points are going to be transformed to a new set of points based on the transformations that are given. Okay, you want to get familiar with mapping notation, since you will be using this method to graph all the new functions you will be learning in this course. So make sure you are paying attention. So here's our second example, and I'm just going to hide the graph. Okay, so in the second example, we're actually going to be graphing using mapping notation. So in example 2, it says, given the following quadratic function, f of x equals negative 2x squared minus 4x plus 3. You'll notice that it's actually written in function notation. So instead of writing y equals, we wrote f of x equals. And the first thing it asks us to do is to rewrite the function in vertex form. Now, fortunately, we've already done that, and we did that in example 1. So if you think back to what the equation was in vertex form, I believe it was f of x equals negative 2 bracket x plus 1 squared and then plus 5. I'm just going to check to make sure this is right. And it is. So negative 2 x plus 1 squared plus 5. So I did that intentionally. What I want you to recognize is if the equation is in standard form, you cannot use mapping notation. You have to make sure it's in vertex form first. So part A is done for us. Okay, in part B it says, in words, describe the transformations that were applied to y equals x squared to obtain the new function. So we want to know what the transformations were that were applied to y equals x squared. So I'm going to start from the left-hand side, and I'm just going to move across the function. And each of the different numbers and signs apply a different transformation to the y equals x squared graph. So I notice that there are actually 4 different transformations that are being applied, and I'm going to describe each one of them. Okay? So starting with the first one, the negative here, what that does to the graph is that it vertically reflects it along the x-axis. So instead of the parabola opening up, it'll open down. So the first transformation is a vertical reflection in the x-axis. Okay, so that makes the parabola up and down. And I guess I can just move this to make it easier to work with. The second transformation that you'll notice is a vertical stretch by a factor of 2. Multiplies by 2 will make the graph stretch. So this is actually a vertical stretch by a factor of 2. By a factor of 2. And then we have a horizontal shift, and this is a horizontal shift to the left, 1 unit. So horizontal shift to the left, 1 unit. And finally we have a vertical shift up 5 units. Okay, and then the last part asks us to use, so I'll just move this here for 1 second. The last part asks us to use mapping notation to graph the function. Now, I don't want you to see the graph, so that's why I'm moving it. But we are going to use mapping notation to actually graph this, and I'll show you the method that we use to graph using mapping notation. So in part C, what you will need to remember are the different transformations that are being applied to the function. Okay. You also need to know what the key points are for a quadratic function. So for a quadratic function, if we just do a quick little sketch, for a quadratic function, remember what the base graph looks like. It's a parabola that opens up, and normally the vertex is at 0 and 0. Okay. As you shift the graph left and right, or up and down, or as you change the stretch factor, whether you stretch it or compress it, the shape of the function will change and the location of the vertex will change. So what we need to think about is what transformations will affect the x-coordinate and what transformations will affect the y-coordinate. Okay? So that's what mapping notation looks at. The other thing we want to think about are what the key points that we could use to actually transform this base function. Now, the original key points that I would use include the vertex, and they also include a couple of points to the left of the vertex and a couple of points to the right of the vertex. And the idea there is so that you can get the U-shaped curve of the quadratic relation. The important part of a quadratic relation is that U-shaped curve. So if I look at a couple points to the left, I would be looking at an x-coordinate of -2 and -1. And if I look at a couple of points to the right, I'd be looking at x-coordinates of 1 and 2. So now this will give me the curvature that's here. I can solve for the corresponding y-coordinates by just using the y equals x squared function. So -2 squared is +4. -1 squared is 1. 1 squared is 1. 2 squared is 4. Okay? Be careful with these values. You can see that they're positive here, but sometimes it's easy to make that mistake. Remember that any negative number squared or any negative number multiplied by itself will give you a positive result. Okay, so just something to think about. So these are actually the key points we're going to use from the base function. All the transformations that happen are going to be applied to these particular key points. So now let's go back to our problem. So first thing I'm going to do is I'm going to start with my key points. The ones we just mentioned. So I have x and I have y equals x squared. That's the base function. That's the function that we normally start with for a quadratic relation. And then transformations are applied to it, which will change where it's located and then the shape of the graph as well. So I'm going to use a couple of points to the left of the vertex and a couple of points to the right of the vertex. I can solve for the y coordinates by just squaring the x coordinates. So that gives me 4, 1, 0, 1, 4. And these will always be the key points for a quadratic function. Now, this is the mapping notation part. We're going to map these points into a new set of points. And those new set of points are what we're actually going to be graphing. So what I need to think about is how the graph is being transformed. Now, the x-coordinates can only be affected by any sort of horizontal transformation, whereas the y-coordinates will only be affected by any sort of vertical transformation. So if I think back to my transformations here, the only transformation that was horizontal is a horizontal shift to the left 1 unit. Okay? And so what that would mean is I would take the entire parabola and move it to the left 1 unit. As I move the parabola to the left 1 unit, I'm actually decreasing each of the x values by 1. And so if I'm decreasing the x values by 1, I'm essentially just subtracting 1 from all the x values. This is the new mapping formula for my x coordinates. Now let's think about the y coordinates. The y coordinates actually have a lot more transformations that are applied to it. And if you notice here, there's a vertical reflection, which means all the y values that were positive are now going to be reflected. So normally they're opening up. They're going to be reflected and open. Oops, that didn't work. They're going to open down. And so what that means is all the positive y values will now become negative y values. And you can see that they become negative y values because of the negative that's at the front here. In addition to that, what's happening is that the y values, or the graph, is going to be vertically stretched by a factor of 2. And so what that means is all the y values will be twice the amount that they were before. So that's another thing that's going to be affecting the y values. Okay? So far what we have is that the y values are going to be multiplied by negative 2. That will make it reflect, and the 2 will make it stretch. Remember, these are all vertical transformations. That's why they're affecting the y value. Finally, what's going to happen is we're going to shift the entire graph up 5 units. So that's the last vertical transformation that we have, a shift up 5 units. So that means we're going to take the entire graph after all the transformations that have been applied to it and then move it up 5 units. If you're moving something up, then you're increasing its value by that amount. Here's the mapping formula for the y values. Now that you have your mapping formulas for the x coordinate and the y coordinate, all you do is you apply to the x coordinates and the y coordinates of your original quadratic function. So what I'm going to do is take all the x coordinates and I'm going to apply this mapping formula to it. So I'm going to subtract 1 from each of the x coordinates. So negative 2 minus 1 is negative 3. Negative 1 minus 1 is negative 2. 0 minus 1 is negative 1. 1 minus 1 is 0. 2 minus 1 is 1. Okay, these will be the points for the new x coordinates of the transformed function. Okay, so this is where that's where these x values have moved to once you shift the graph to the left one. Okay, so let's look at the y coordinates. I'm going to multiply them by negative 2 and then add 5. So negative 2 times 4 is negative 8, plus 5 is negative 3. Negative 2 times 1 is negative 2, plus 5 is 3. Negative 2 times 0 is 0, plus 5 is 5. And then the values here should repeat since it is a symmetrical parabola. Negative 2 times 1 is negative 2, plus 5 is 3. And negative 2 times 4 is negative 8, plus 5 is negative 3. Okay, so these are all the y coordinates that we are going to have based on the transformations that were applied to the original y equals x squared graph. Now I can graph this just to show you what it'll look like. And so I'm just going to draw my grid here. And one of the things I'm going to point out as I'm drawing the grid here, one of the things you will notice is, remember where the vertex of the original quadratic function was? It was at 0 and 0, right? Now, as you apply the different transformations, you'll notice that the vertex has moved to negative 1 and 5. If you think back to the previous question, or even if you look at the original function that was up here, you can confirm that the vertex is indeed at negative 1 and 5. So these mapping formulas definitely worked. Okay, all they have told me now is where those points have moved to. These were the original points for the y equals x squared graph. Now they've moved to a new set of points. So if I graph this, I have a point at negative 3 and negative 3. I have a point at negative 2 and positive 3. I have a point at negative 1 and 5. 0 and 3. And then 1 and negative 3. And I'll just sketch a curve through those points. And there's a function. And luckily, once you have a function in function notation, instead of having to write out the entire function, because f of x is a definition of it, you can just label it as f of x and not have to worry about writing out the entire thing. That's another benefit of function notation. Okay, so there you have it, a graph of a quadratic function using mapping notation. And again, you can